let's suppose that instead of just one first order ordinary differential equation, we just have a few of them which are connected and coupled. So in this case, we have a system of m first order ordinary differential equations. And this is the system, this is the representation of this, the system of m first order differential equation. We have m equations like that. So we have m y functions from y1 to the ym. For example, here we have the first equation corresponding to the function y1, which basically means that's the first order ordinary differential equation. So here we have, using the same structure we consider for the when we just had one equation. Here we have that the time derivative of y1 it's equal to some function. We're calling that f1 because we are going to have like m different functions. And this function will depend not only on just t and y1, but will depend, as you have a system of different y functions, it will, in general, it can depend on time, y1, y2, and so on until ym. And besides the equation, as we had for the first, when we just had one equation, we have one initial condition corresponding to this y1 function, which basically means that y1 evaluated at initial time has some specific value that here we are representing by y1 over naught. So that equation corresponding to the first function, y1. We have another one for y2, and so on and so forth, another one for ym. So that's a system of m different first order ordinary differential equation. And how can we solve numerically whenever we have such a system? That's quite easy, especially after considering the numerical methods for just one first order differential equation, because here, in order to solve that equation, we can just generalize any method that we have considered for just when we had just one first order ordinary differential equation. And the only thing we have to do here, as we have m different functions, we have to apply the method to all the different equations. So it's like we had to apply the method, like in this case, m times for m different equations. And actually we can summarize and write, and we can generalize the method for such a case, just adding another subindex, which in this case we are going to call it j, and j is going to run from 1 to m, and this subindex is going to identify the wave function that we're going to have. Okay, so for example, let's have what's the numerical receipt whenever we are considering the forward Euler method, when we have in the case that we have m and the previously considered m first order ordinary differential equation. This is the expression that will summarize this method in this case. And as you can see here, here in any y function we are having like two different subindexes. Here the first j1 is identifying the function we have, and this j will run from 1 to m, as we have said before. And the other one, the one in green here, the I or I plus 1, is identifying the time mesh, so the time when we are evaluating the function. So as you can see, that's the structure. So basically here we have, if we want to evaluate, that's the y j function evaluate at time I plus 1, it's equal to the yj function evaluated at time I plus this function, which corresponds to the time derivative of the yj function, which in this case is we're calling that fj, and this fj is going to depend in general on time and the different y1 to ym functions, all of them evaluated at time I, plus delta t. So that's basically, as you can see, the forward Euler method, for example, for a system of first order ordinary differential equations. So basically, in a loop, in a time loop, you have to consider like m different equations in order to specify the value of all these m different y functions we do have at the next time, once we know the value of all the different y functions at time I. So as you can see, it's quite straightforward whenever we know how to apply that for whenever you have just one first order ordinary differential equation.